Okay, index sequential access and prefix B plus trees. So there are two kinds of access to any given data file. There can be a sequential access for a data file or an index access to the data file. Sequential access to the data file simply means that we're going to access the record one after the other in the sorted order of the based on the primary key. That is a sequential order or the sequential view. Index view is where we keep the data file as entry sequenced and we only are going to access the particular records based on the index value. So that is the index view of the particular file. So there are two kinds of views, index view and the sequential view. And index view is generally used for random access. If you want just one random record from thousands of records, then an index view is definitely better because we can simply look for the given record in the index file with the primary key, and then we know what is the RRN of that record and we can seek to this location in the data file. So index view is mostly better for random access, whereas sequential view is required when we have to access all the records one after the other in the sorted order. Now what we've concluded up until now is sequential ordering or sorting the entire records of a very large file is absolutely unnecessary, and it's because it's very tedious, especially during the maintenance when new records come in and existing records get deleted. Inserting something in between or deleting something in between is a very tedious task. So which is why we have only kept our data files as entry sequence, and we maintain the entry sequenced data file via an index file. Now, what if we need to access all of the records in our very large file in the sorted order? Does our index file allow this? Yes, it very much allows this. So, if I have to access the record number 1, or taking an example as a student record or a student file and taking the primary key as the USN number, when we look into our index file, we know that the first entry is USN number 1 and we know the RRN of this record. The RRN of this record could be anything, any random number. It could be, say, the 9000. It could be a value 9000. So we can seek to this location 9000 and fetch the record number 1. So when we look for the second entry in our index file, that could be an RRN 3000, which means record number 2 is at a location 3000 in our data file. So we can seek back from 9000 to 3000. And then we have to go to the record number 3. We simply have to seek to the location as pointed to by our index file. Say that could be 4000. So from 3000 we have to now go to 4000. So sequentially accessing the records one after the other based on the sorted order is still possible via from the index file, but that's a very tedious task simply because it involves seeking, and seeking is extremely expensive for us. Now, in this situation, we are considering dual mode applications wherein we want a support for random access. Randomly, if you want any file, any record in the file, we should be able to quickly go to that location and pick up that record. We want that kind of facility also, which is given to us via indexing. And we also want another facility wherein if you want to process all these records, all the 10,000, all the 1 lakh records together, one after the other in the sequential order, we should still be able to do that. So what kind of facility can we offer for such dual mode applications is our question, right? An example of such dual mode application is a student record system at university. Probably you want to fetch some random student information, then yes, we need that support via indexing. And suppose we want to process all the student information one after the other to check who has paid the fees or to check what is some penalty or something like that, then even such a flexibility is required. So we're talking of the facility provided for such dual mode application, right? So now for now, let's pause what we're going to do about the index part or the index part. We'll see what is going to happen for the sequential set. So there are two keywords for us here. One is the sequence set, another is the index set. Index set simply means that the primary keys of all the records along with the RRN. We're going to pause that for a while. What we're going to do about the index set, let us now concentrate on the sequence set. Sequence set is the collection of all the records in the data file in the sorted order, right? How are we going to maintain this? Maintaining the sequence set simply means that, okay, you have 10,000 records currently, a new random record comes in which has to go into the 3000th location. How are we going to manage that? Or a record at the position position 5000 is deleted. How are you going to manage that, right? So maintaining the sequence, and how is it even possible? We've discussed this in the earlier chapters that if we have thousands and 10,000 and lakhs of records, and we have to, shift all the records, making space for the new record, or deleting some record and putting all the next records into the previous location, that's a tedious task. So we don't want to do a whole lot of changes. What we want to do is we want to localize the changes. So we need some flexibility where we can localize the changes, so which is why we use the concept of blocks, which means even though we have 10,000 records, we're going to put some set of records in one block, another set of records in one block. How many records are you going to put in one block is a decision by you as a file structure designer, because block size is variant, it's never fixed. But we need to take care that the block size is a match between the size of the block, and there is a size of the buffer, right? Because all the records in one block should fit into the main memory at once. So that's a basic requirement for us. So, but otherwise we can decide what should be the size of each and every block. Size of each and every block is the number of records that goes into that the number of records that actually go into the particular block, right? So that could be any number of records. Now these blocks, a given file with 10,000 records can have n number of blocks depending on your blocking factor, right? Depending on your blocking factor. Now these blocks, these n number of blocks need not be present next to each other physically on our hard disk. A block number 1 could be at one location, a block number 2 could be at another location, block number 3 could be at another location. So we need a linked list kind of arrangement between the blocks. So which means you're going to link one block to another block to another block in the sequential order. Now, how are we achieving this localizing? Which means if we don't expect that the block is completely full every time, yeah, there is a possibility that the block is full. So you restrict, there are 5 records in one block and the 5 records are already there, right? And which means you're actually specifying a range, right? How do we specify the range? I'm going to tell you that. So we specify a range telling, yeah, from here till here, all the records go into this block. From here till here, all the records go into this block. So there's always a possibility there is a block overflow, right? There's the block could fit in 5 records and the 5 records are already there. And now you're having a situation where a new record is coming in. So how do you deal with that? Dealing with this block overflow, or dealing with the block underflow, where you expect that there is some minimum number of records in the block, but such a minimum number of record is also not there in the block. So how do you deal with this block overflow and underflow is very similar to how we deal with the nodes or the page overflow and underflow in the case of our B tree. What do we do in our B tree? We define the order of the B tree page, right? We say M could be 4 or M could be 5, right? If I say M is 5, then the maximum number of records in that particular page is 5. What is the minimum number of records? Is M by 2, which is 2. At least we expect at least 2 records are there. If there is not even 2 records, then that's an underflow situation. What do we do in the case of underflow? We try to merge it. See, this particular page or this particular block is an underflow, so you cannot leave it like that. You have to merge with the previous block or the next block, right? So that's what we do. If the block is overflow, then we don't try to put the contents of it into the next block, right? So we don't try to do that. What we do is we split that block. So if there's only one block initially, we're going to split that and make it into 2 blocks, taking care that each and every block is at least M by 2, right? So it's the same concept of handling with block overflow and underflow as well. But why should you bother with block underflow? Just think about why you should bother with block underflow. We say that minimum, if the block size or the blocking factor is 4, we expect that at least 2 should be there, at least 2 records should be there in each and every block. What happens if there's only one record? What is even the difficulty, right? So you must remember that whenever we bring in a block, we try to put that in the main memory, and block underflow is an ultimate wastage of memory, right? We're simply bringing an entire block to the main memory, but there's only one record in that, and that is really inefficient. So we should take care of handling with block overflow and underflow as well. Now we would understand this better with this particular diagram. So let's see the A part of the diagram here, wherein we have wherein we have okay Okay, wherein we have three parts of the diagram A, B, and C. In the A part of the diagram, we can see three blocks: block 1, block 2, block 3. So the blocking factor here is 4. So the first block here has 4 records: Adams, Baird, Big C, and Boone. Right, and block number 2, it's linked to block number 2, which means block number 2 is need not be physically adjacent to block number 1. It's linked to block number 2. So after block number 1, the next record that will be accessed is Bynum, Carson, Cole, Davis. After block number 2, there's block number 3. We observe that block number 3 is not overflow, but it's not underflow as well. There is at least 2 records there. That's the A part of our diagram. What's happening in the B part of our diagram is there is an insertion, right? There's an insertion that's happening, and the insertion is of a record called as Carter. The entire record is not shown here. Please observe that we are only showing the primary key of each and every record. So where would Carter go? Observing the figure number A, Carter would definitely go after Carson, right? But block number 2 is already overflow. So what do we do with the overflow situation when a new record comes in? How do I know that Carter goes into block number 2 and not into block number 1 and block number 3? It's simply because, we are sorting it, right? We know that all the records from Adams till Boone, whatever is that will go here, and then I have a delimiter from Bynum till Davis is going to come here, then Denver till Ellis is going to go to block number 3. A new record is coming in, which is Carter, should definitely go into block number 2, right? So because it's a sorted order, and since block number 2 is already overflow, what we simply do here is we split block number 2. So when we split block number 2, observe the figure number B, we have split block number 2 into 2 parts, block number 2 and block number 4. Why block number 4? Because block number 3 is already present. So the first 3 records, Bynum, Carson and Carter is a new record, and Cole and Davis is the other 2 records which were already present. So observe the links here. After block number 2, the link is to block number 4, and then from block number 4 to block number 3. So which means even though they're not physically adjacent, we know the logical order in which the block should be accessed. After block number 2, we should now access block number 4 simply because block number 4 is the next block of block number 2. Right, and then after block number 4, we have to access block number 3, something like that. Now that's the figure number B. Now let's observe what's happening in C. So what we're doing in C is we have a deletion of Davis, right? Say deletion of Davis. Where should Davis be deleted? You know that observing figure number B, Davis is deleted in block number 4. As soon as Davis is deleted in block number 4, we see that there is an underflow. So there is an underflow simply because minimum 2 records should be there, but it has become only 1 record there. Now whenever we see that whenever there is a deletion and there is an underflow, we have to do the merging. So where is the merging happening here? So whatever was there in block number 3, right, whatever was there in block number 3 is now shifted to block number 4 because that's a previous block, right? So we shift whatever was there, Denver and Ellis, to what we call as block number 4. There is space for that. Now there is a possibility there is no space in the previous block as well, or we check for the next block. So that kind of rearrangement should be done whenever there is underflow, right? So now here in this figure number C, we observe that the block number 3 is available for reuse. So the next records which come in can go into block number 3. So that's a kind of block arrangements we do for the sequence set. So I repeat, sequence set is the collection of records in the sorted order in our file, right? Now what do we do with the sequence set? We don't group them as one whole thing. We divide them into parts. The division of the records into parts into blocks, so that we localize the changes, right? We don't want to change. So if something is getting inserted, it's getting inserted in only one block. We don't bother to disturb the other blocks. If something is getting deleted, it gets deleted in only one block. We don't bother to disturb the remaining blocks. But when insertion and deletion happens in one block, there can be block underflow and overflow. Then we try to minimize the changes. We just try to make the changes in the adjacent blocks. We don't try to make the change whole together in all the set of blocks. So that's how we are trying to achieve efficiency by localizing the changes. Now the next thing is choice of block size. So what should be the choice of block size? That's what should be the blocking factor. How many records should you place in one block? A block is the maximum guaranteed extent of physical sequentiality, which means when you bring a block to the main memory, the number of records in that block is the maximum allowed sequentiality, after which you definitely have to seek to the block number 2. Block number 2 is definitely not going to be immediately adjacent to block number 1 physically. They're just logically adjacent. After that, definitely we'll have to seek to block number 2 and bring in the records from block number 2 to main memory. So the maximum guaranteed extent of physical sequentiality is just one block. So what should be the maximum size of the block? So does it mean that if we have a very large block size, I can bring large number of records to the main memory at once, so that's better? So can we conclude that? Not really. So we should be careful of doing that. We have to consider two things. So consideration number 1 is we should be having the block size in such a way that we just don't bring in one block at once. We have space in our main memory to bring multiple blocks at once. Why do I need multiple blocks? So if I'm bringing block number 2, I should be also be able to bring in block number 1 and block number 3 along with it. Why? There's a possibility when I operate on block number 2, I may have to make some changes in block number 1 and block number 3 because of overflow and underflow, right? So which is why we should choose a blocking factor or a blocking size in such a way that we can bring more number of blocks into the main memory at once. That's a consideration number 1. What's a consideration number 2? See, you cannot have a very large blocking factor or a very large block size so that you bring in a lot of records at once. So that's a very inefficient access, because what if the block size is really large, it doesn't fit in the main memory at once? That means to access one block itself you need multiple trips to the disk. So multiple trips to the disk is very expensive to that, so you have to take care that the entire block is bought into the main memory with just one trip to disk access, right? So careful consideration to the block size must be given. So the next thing is, okay, now we saw what is the best way to deal with our sequence set. Now let's see, we can add a simple index to the sequence set. So in our figure here, figure 10.2, it's showing a sequence of blocks. So it's showing 6 blocks, 1, 2, 3, 4, 5, 6. So in block number 1, we have all the records from Adams to Byrne. Whatever records fall in from Adams to Byrne is in block number 1. Whatever records fall in between Boland to Cage is in block number 2. All the records that are falling between Camp and Dutton is in block number 3. And so on and so forth. So please observe that we're not showing all the records, the entire record and all the fields here. We're only showing the primary keys over here, or we are just showing one field over here. We're not showing all the fields of the record over here. Now we can add index to this. What do I mean by indexing? So I need references. I need references to each and every block. What's a reference to me for block number 1? Probably the last record field, which is Byrne, is the reference to me. What is a reference to me for block number 2? The last record primary key, or the last record's reference, which is Cage, is block number 2 reference. And block number 3 is Dutton. Block number 4 is Evans, and so on and so forth. So we can add a simple index for this kind of blocks to us. So what's the advantage of this? So how do we add, what is the advantage of indexing? You know it very well. We bring in only the index to the main memory. Now the user says with this 10.3, figure 10.3, assuming that 10.3 is in the main memory as of now, what we do here is, let's assume that the user wants some record with the primary key as Faber, right? So what do? You look for the first option, Byrne. No, it's Faber is greater, and Cage is also Faber is greater than Cage, Faber is greater than Dutton, Faber is greater than Evans. And then when you say Folk, okay, it's less than Faber is less than Folk. So you can definitely look into this particular block number 5 for a record with the primary key Faber. It's something like that. So we know which particular sequence set block to access via this index set. So this particular slide here is showing us both the things. It's showing us sequence set in the figure number 2, and it's also showing the simple index in figure number 10.3, right? So we'll see how to deal with that. Now coming to indexing, right? So indexing is a whole lot of story which we have seen in the last chapters. How big can be this index file? Now, considering an index file like in 10.3, the size of this index file is the size of the number of blocks. We don't know how many number of blocks can be there. The number of blocks for a file depends on the number of records in the file and also the blocking factor. Now, if I consider millions of records in a file, then I'll have so many thousands and lakhs of blocks, and I'll also have those many entries in my index file. Now, if the index file is really large, right, an index file is also never stagnant. Whenever some changes happen in my data file, in the sequence set, data file is now the sequence set. Whenever some changes happen in the sequence set, there is a corresponding change in the index set as well. So what do we do in that case? What do we really do in that case? We have to manage or maintain the index set as well. Maintaining the index set when the index set is really large is a very tedious task, because we expect the index set is sorted in ascending order and we'd like to perform binary search, and we've seen all the chapters from chapter 5 till chapter 9, and we've concluded the best way to deal with the indexing set or the index file is B trees, right? So we know that when the index file is really large, it doesn't fit in the main memory at once, the best way to deal with the index file is B trees, right? So the entire index should be held in main memory, right? If it's not possible, then we have a difficulty. The next point, index must be updated. Index is never stagnant. Whenever the block sequence set is changed by splitting, merging and redistribution, the corresponding index set also changes. So that's again another thing. The index may be very large. How large, we don't know, depends on the size of the file, and it does not fit in the main memory at once. So what is the best way to deal with the index file that we know so far is B trees. So what we do here is we have a sequence set, and now we are also have an index set, and we are going to maintain the index set as a B tree. So what we do is we use B tree for the organization of the index for the sequence set of blocks. The resulting hybrid structure is B plus tree. So B plus tree is where we have B tree index plus the sequence set of records. What is sequence set of records? Grouping of the set of records in different blocks is the sequence set of records, and maintaining the index of the sequence set records via a B tree is the B tree index. So the combination of these two, which is a hybrid structure, is what we call as a B plus tree structure. Now, what should be the content? Now, so that is our B plus tree. B plus tree is the sequence set plus the B tree index. So what should be the content of the index, right? So why should we actually use the keys? So if you observe, getting back to this diagram, our index file had the actual keys. Burn was the actual key, cage was the actual key. Why do I really need them, right? Why don't I use some other kind of separators? What are separators? So here in this figure number 10.5, you can see two blocks, block number 3 and block number 4. Block number 3 having all the range of records ranging from camp till Dutton. We have all the records from Embry till events in block number 4. What's a separator between these two blocks? Any sequence of characters that differentiate between these two blocks is a separator. For example, DUTU. So anything that is DUTU and that is equal to DUTU or less than DUTU goes to block number 3, and if it's greater than that, it goes to block number 4. And similarly, any other DZ. If I say DZ, so anything that's less than DZ goes to block number 3. Anything that's greater than DZ goes to block number 4. So on what basis should we use the separators, and why do we need the separators, in fact, is a question, right? So we need not even have the actual keys, right? We can have something less than the actual keys. An actual number of characters in the keys could be larger than the separator we require, so we try to save space on that as well. We don't even have to keep the entire field or the entire number of characters in the particular index file. We can reduce the number of characters in the primary key field. So we are now seeing what can be used between us. So separators, what are separators? They are not the actual keys. They are just a sequence of characters that are just enough to differentiate between the blocks. So they guide us in the choice between the blocks as we search for a particular key. Now we can save space. The ultimate idea is we can save the space by placing the shortest separator in the index structure, which means the index file is of variable length, right? The first entry in the index file could have a separator that has 2 characters. The second entry in the index file could have a separator which has only 1 character. The third entry could have 3 characters. So we are actually okay with the variable length file for the index structure. We are okay with that, but we want to keep the minimum number of characters for the primary key field in our index file. Now observe figure number 10.4. What are the separators we have chosen BO as a separator between block number 1 and block number 2. So anything that's less than BO goes to block number 1, and anything that's equal to or greater than BO simply goes to block number 2, right? And similarly, CAM is a separator between block number 2. And how did we choose this? We'll see how did we choose CAM, and how do we conclude that CAM is the best possible shortest separator between block number 2 and block number 3, right? So anything other than that will have minimum number of 3 characters only. Anything cannot have less than 3 number of characters. Coming to block number 3 and block number 4, in this diagram there's only E, right? So anything less than E definitely falls in block number 3. Anything greater than E falls in block number 4. So we need these separators. So in our previous discussion, when we saw, we kept the actual primary keys as separators. Herein we are telling, look, we don't need the actual keys, we can keep something less than the actual keys. Why? We want to save space. Our goal is to better utilize the space. Now the relation of the search key and the separator is, if the given key, if the user is searching for a key and if the key is less than separator, if the user is searching for Adams, you compare with the first entry in our index file, which is BO, and Adams is definitely less than BO, which means you have to go to block number 1. Say for example, the user is searching for a record with the key Gaddis, right? So which means you check for the first entry. So BO is definitely smaller than Gaddis. So you go ahead, then you look for CAM, it's greater, E again it's greater, F is again greater, and Folks, yeah, Gaddis is greater than Folks, and you definitely access the, since that's the last entry, so you definitely access the block number 6, right? So if the key is less than the separator, you go left. If the key is equal to or greater than, then we go right. So that's how the separator guide is telling which block should we actually access. Now how do we find the shortest separator? Now this is very important from the exam point of view. You could be asked, how do we find the shortest separator? Or design a function to find the shortest separator between the blocks. Now there are 3 parameters to this particular function, key 1, key 2 and separator. Right, so key 1, it is the key 1 of the particular first block. Let's assume block number 1 and block number 2. So the last key or the last records key and the first records key in block number 2 is key 2. So key 1 and key 2. Key 1 is the last records key in block number 1 and key 2 is the first record key in block number 2, and separator is what we're trying to design. So we are now running in a loop. So separator, we are designing the separator. We say separator is equals to key 2. So the first character of your key 2 becomes a separator initially, and then you go ahead. So you just put one character in the separator as of now. And if key 1 is not equal to key 2, if we find a dissimilarity between those two, then we immediately break. That's the endpoint of that, right? And or if the key 2 is that's the endpoint of our key 2, then we again stop at that point. Otherwise we increment both key 1 and key 2. For example, right, so for example herein Burn and Bolin, so our first character is B, so that becomes a separator, and then we go ahead, E is the next character in key 1, O is the next character in key 2. You compare E and O, and then you say O should go into the separator, and then you go ahead, and when you go, before you go ahead, you check E and O, they're already different, right? As soon as they're already different, that's the endpoint for us, right? Now let's see Dutton and MD, block number 3 and block number 4. When you observe D and E, so your separator says the first character in key 2, which is which is the first character that goes into the separator, and then you compare D and E. D and E are already different, so that's what this code is really telling us. If key 1 is not equal to key 2, then please stop at that point, or if key 2, the number of characters in key 2 is also over, then please stop at that point. Otherwise keep incrementing. So with this particular function, and at the end we have a null character because it's a string, and definitely it has to terminate with a null character. That's what we're trying to do. So this particular function is helping us to design to find the shortest separator between the blocks. Why do we even need this? Look, that's only for saving the space. It's not necessary that we design something like this for B plus 3. B plus 3 is already defined by us. Whenever we have a sequence set of blocks, and then we have an index to that sequence set, and we maintain the index set as a B tree. How do I maintain the index set as a B tree? You know that very well, right? So we define the order of the B tree, we define M as order of the B tree, and we go on putting the records into the pages of the B tree, and whenever there is an overflow in that page, we split it. Whenever we split, we have to create a new level, and we always create the B tree from the leaf level to the root level, right? So it's similar to that. Now the question here is, we don't want to use the actual key, so we want to use some better separators, which is why we did that, right? That's not even required. If I'm actually implementing B plus tree, I need not restrict to finding a best separator. If I'm finding a best separator, then such a B plus tree is what we call as a simple prefix B plus tree. I'm not going to call that as a B plus tree. I'm going to call that as a simple prefix B plus tree. Why did I call that as a simple prefix B plus tree? Is the separators are not the actual keys. The separators are the shortest possible characters that separate between two blocks. So that's why that becomes a simple prefix B plus tree. So if I ask you what's the difference between B plus tree and a simple prefix B plus tree, you must be in a position to differentiate between those two. Now let's observe this figure 10.7. There are certain set of separators. Let's observe it from bottom to top. So there are 6 blocks here, and the range of records are shown over here. The best separator or the shortest separator between these records are also found out, and we are showing the index set now. Now what is this index set? Index set is a B tree. And what do we need of a B tree? We need an order for the B tree. We are assuming here the order of the B tree is 3. The order of the B tree is 3 with a restriction that there are 3 links but 2 data fields, right? Please observe that the index set here has maximum 3 links and 2 data fields. Now block number 1 and block number 2, the separator here is BO, block number 2 and block number 3 CAM, 3 and 4 is E, right? So as soon as E comes in, what do we have to do? To the first entry in my index here, or the first page, which is BO, CAM, E. E is an overflow record, so we split it in such a way that in such a way that because there can be 2 entries, so one entry is still not an underflow, so E goes into the next page, right? Next F comes in, and then folks also come in, so as a separator, so we have created another level. So BOCAM is, and F and folks are in one level, and E is the root level. Now herein, please observe that each node contains n separators, but there are n plus 1 branches, right? N separators, the number of separators is 2, so the minimum number of separators in each and every node of the index set or the node of the B tree is 1, right? So that's how we do. Now if somebody gives you this structure, now this is a B tree index set, so which means you should understand in our main memory we'll have only this page which has the value E. And you also know with the reference to the left block, the reference to the right block. Now somebody says, fetch me a record with probably Faber, right? Fetch me a record with the primary key as Faber. So what do you do when you have the root page in the main memory? You compare Faber with E. You realize that Faber is greater than E. So you go right. And when you go right, you bring in this particular page which is a right child of E. So you have F and folks, 2 particular separators. And you compare Faber with F, and you realize yes, F is greater, so whenever it's greater or equal to, you follow the right link and you definitely bring in block number 5. When you bring in block number 5 is the sequence block, right? So you bring in this block to the main memory, and when you bring in this block to the main memory, you have all the records ranging from Faber till folk in your main memory, and you can operate on them. You can present it to the end user, you can do some changes and then reflect it back. So that's one thing that's happening, right? So that was the same diagram there, right? So now let's see, that's a simple prefix B plus tree for us. Now let's see how do we really maintain this prefix B plus tree. There are 2 possibilities. The first possibility is the changes are localized to single blocks. How many blocks are there in the sequence set? There are 6 blocks. There is a possibility that the changes are localized. I delete something and that deletion does not disturb any other block. So I'm taking the case number 1 over here. So whenever there is no change in the sequence set, then definitely there is no change in the index set as well, right? So but that need not always be the case. There may be some cases where insertion happen and splitting of the sequence set block happen. Why do we have to split the sequence set blocks? Whenever there is an overflow, we don't have overflow and underflow only in the index set. We have overflow and underflow both in the index set as well as in the sequence set. But the sequence set contains the entire record, whereas the index set only contains the primary key, or in fact only the shortest separators between the blocks, right? So whenever there is splitting because of insertion or merging because of deletions, then the index set contents also changes. So in this diagram here, figure 10.8, there is a deletion of Embry and Folks, right? So where is Embry deleted? So we have only the root record, we have the reference of only the root record or the root page in the main memory. So when we have to delete Embry, we go right, and then we go bring in the next right child of E, and then we go left. Yeah, and that means block number 4. So what happens to block number 4? We delete something in the block number 4 and nothing really has happened, so we're okay with no changes. Next, we're deleting Folks. So what do we do with deleting Folks? You go from the root page to the right child, and then you greater than or equal to, so you bring in you bring in the you bring in the 6th block there, and you delete that particular record from block number 6. But what about the separator? The separator here was Folks, right? The separator here was Folks, and you don't bother to change it. Sometimes it's not necessary to really change the contents of, you may have to change the contents of the index set, but if it's unnecessary, then we better try to avoid it, right? Now that was the case number 1, where we deleted something and we inserted something, or we tried to do some changes to the sequence set, but there were no splitting or merging. When there is no splitting or merging, we don't have change in the index set. Now the second case is where we have changes involving multiple blocks in the sequence set. What if we have multiple blocks the changes are reflected in multiple blocks in the sequence set? In that case, we have to change the index set. What do you mean by changing the index set? Something may be changed, something may be added, something may be deleted. And whenever something gets added or deleted in the B tree, we know there can be splitting, merging, and redistribution in the B tree as well, right? So we need to take care of that. So there is case 1 and case 2. This the diagram here 10.9 is case 1. We're showing the cause of a split. So we are inserting into block 1. We are inserting something into block number 1 here. That's a previous diagram. So there were 6 blocks, and now we added something to block number 1, so it's causing a split. Because it's overflow, it's causing a split. So which means block number 7. Please observe, block number 7 has come into this picture simply because we split the number of records of 1 into 1 and 7. So logically, even though 7 is physically never adjacent to 1, we link it in logical way. So after 1, it should be accessed as 7, and after 7, 2, and so on and so forth. Right? Now, what was there in our page, in our parent page? BO and CAM. But a new separator has come in, which is AY, right? So AY, BO, CAM is not allowed because the number of separators allowed is only 2. When AY comes in, we need a separation, right? So AY, and that's a separation here. AY has come over here, and BO and CAM has gone to the next place, and again it's gone to the next level. So we are dealing with the insertion and deletion causing splitting and merging, not only in the sequence set but also in the index set, right? So that's what we're trying to do, and we split AY, and then we put BO and CAM in the next record. BO, CAM, and E, that's not going to work. So BO and it's gone to the next level, and CAM alone is over here, and this part is unchanged. Block number 4, 5, and 6 is not changed over here. So there is a change in the sequence set, so which means there is a corresponding change in the index set as well. Case number 2 is where we are deleting a record from the block, causing a merge. So please observe 10.10. We're deleting from block 2, and it's causing underflow, right? So it's and the consequent merging of block 2 and 3. So in the previous diagram, there were 2 blocks, 2 and 3, and there was something deleted in block number 2, so we are merging block number 2 and 3. So which means this separator CAM is no more required, or no more required to be present over there at all. So we have to merge, right? So in this case, again, the merging of the sequence set here is causing a merging of the index set as well. So we brought them down, right? So the previous here had BO and E in the root page. Now here it has only E. BO has come to the left page. So we have such rearrangements not only in the sequence set but also in the index set. So please observe these points. Changes to the index set are secondary. Changes don't happen in the index set at once. The first changes are reflected in the sequence set, and changes in the index set are a byproduct. Only if it's required, then we change the index set. So how do we do the changes in the index set? If there is a splitting, then we add a new separator. If there is a splitting of the blocks, then we need a new separator. If there is a merging of the blocks, then we remove the separator. If there is some redistribution of the sequence set, then we have to change the value of the separator. Node splitting and merging. Now splitting and merging can happen in the index set also. So the node splitting and merging has to propagate until the root level up to all the higher levels of the index set. So that is the concept of B plus trees. Now the next thing is index set block size. So we spoke something called as the block size for the sequence set. What should be the block size for the index set is the question. What should be the number of separators, or what should be the number of characters possible in the index set page or the index set node or the B tree nodes? So ideally the block size for our index page as well as the sequence set page, they are the same, right? We don't change, we don't keep a different page size for the sequence set and different page size for the index set. We say we keep the same thing simply because of these three important reasons. We need a good fit among the block size and buffer size. So we have the best block size already defined. Why do we change that for the index set? We're going to keep the same thing. We want to implement better buffering schemes so that's possible with a better block size. And index set block size and sequence set block size are often, they're not two different files. They're not absolutely two different files. The sequence set and the index set together, they are actually one data file only. So we don't want to keep different block size for these two. So index set and the sequence set both have a common block size. Alright, so the last two things I want to tell you: internal structure of the index set blocks. So what should be the structure of the index set blocks? Structure of the index set block is the structure of a node. Structure, what does a node have? A node has separators along with the links. In our actual B tree, we don't have separators, we have the keys only. But herein, since we are doing simple prefix B plus tree, we don't have the keys, but we have what we call as simple prefixes. So we can have a better arrangement over here simply because the number of separators in one node of the B tree need not be the number of separators in another B tree. We want a variable length B tree. We need not have a fixed length B tree. If we have a fixed length B tree, the whole arrangement, the whole idea we did, look, we need not have the actual number of characters in the keys. We can have lesser number of characters in the keys. So the idea was to accommodate more number of separators in one node or in one page. So we don't have to have fixed order. We need variable order B tree. Now this is conceptual. This is not expected for you to implement in your mini project. In fact, in your mini project, you can implement B plus tree. Nobody is asking you to do simple prefix B plus tree. We directly use the keys as the separators. But in case we're using simple prefix B plus tree, then we need to better have a variable order B tree. Now variable order B tree is very complicated in the sense we need our own methods, our own restrictions telling when is the block overflow or when is the node overflow. We cannot say, yeah, there are 5 separators, now the block is overflow. You cannot tell that because the number of characters is what really matters, right? So we need better functions to deal with overflow and underflow in the case of shortest length separators and variable order B tree. So in case we are having a variable order B tree is, we don't say only these many separators should be there in one particular node. There can be any number of separators in one B tree node depending on the size of the B tree node and the number of characters in each and every separator. So here is an example: variable length separators and corresponding index. So AS is one separator. Observe figure number 10.2. 0.11, AS is one separator, BA is one separator, and what we can do is we can have an index to the separator. So 0 0, if you go to 0 0, then you fetch the first separator. If you go to 0 2, you fetch the second separator. If you go to 7th location, then you fetch the fourth separator. If you go to the 23rd location, then you fetch the last but one separator. So when we have such an index to the separator, then we can perform binary search. The idea here is even on one node or one page of the B tree or index set, we should be able to perform binary search, which is why we can have an index separator. So how exactly does the structure really look like? So a structure of a variable order B tree index set block can look something like this. I may have a separator count. How many separators are there in this node? That's the first thing. So there are 11 separators and there are 28. 28 is the total number of characters. That's the next information. Then the actual separators, index to the separators, and relate. What is this relative block number? So if you are accessing AS, then the corresponding block number that you should be accessing, the corresponding relative block number or the relative sequence set block number is B00. Now if you are accessing BRO, then the block number is B02. So we need the whole set of information in a variable order B tree. So the structure of the node of a variable order B tree itself is so complex that we need to define all of these things. What are the separators? What are the index? The index of the separators are local, right? They simply say, we don't have any separation between the separators, right? So within the particular node, which is why we have an index here. The relative block number is where we link the particular separator to the corresponding block in the sequence set. Okay, so conceptually this simply means block 00, observing figure 10.13. So block 00, the relative block number is accessed via the separator AS and the index of that is 0, and the index of 1 is at a location, the block number is B01. It's something like that. Now decisions about when to split, when to merge and when to redistribute it is very complicated in the case of variable order B tree. Now you must know what's the difference between fixed order B tree and variable order B tree. And in our mini projects and in our implementations, we fortunately don't have to implement this as of now, variable order B tree. That's a high level or a complicated approach, but we must understand that if we don't use the actual keys and if we say we need the shortest separator, then we need a support from the B tree also to include variable number of separators in each and every node. If you have a fixed order, then you say only 3 separators are allowed, only 4 separators are maximum allowed, then that's really not going to be helpful to us, right? So that's what I want to do in today's class, and the assignment questions are something like this. The first question is, what are the considerations for the choice of block size? The two considerations which we discussed, right? Block size should not be very small. At the same time, block size should not be so big enough that you need multiple trips to the disk to access the records in one block, right? So you must explain that. That's a simple answer. And C++ function, what you just saw, to find the shortest separator between the sequence set blocks. And that's the second question. The third question, that's a lengthy question. What is simple prefix B+3? And explain the maintenance. The maintenance, two cases. Case 1, where there is no change in the sequence set blocks by insertion and deletion. Case 2 is by insertion and deletion there is a change in the sequence set blocks. Insertion causing splitting, deletion causing merging. So you must explain both of these two cases with insertion and deletion and diagrams. So that's an assignment question for you for today, right? So thank you so much for this.